So last time we um, talk about this stability phenomenon that's happening right below the Turon density, saying that almost extremal graphs, they structurally looks close to extremal graphs in eddy distance, which is sort of intuitive when there's a unique maximizer. Then whatever goes close to the maximizer, meaning that they are almost extremal, they must be looking like the maximizer. And we started last time the philosophy of this so-called very classical approach called the stability method. This is a way of utilizing stability type results. So what is a stability type results? You have extremal problem with the unique maximizer, extremal structure, and any almost extremal one looks like that. So this method is saying, let's recall, the recipe is we take a extremal problem, and the easier result to obtain is, instead of solving this extremal problem exactly, let's try to solve it asymptotically. And then as a second step, we probably can analyze our way of proving asymptotic results and squeeze out stability type results. Then the key part of this stability approach is to use the structural information we obtained from stability to slowly remove imperfection to get exact results. So what does this let's illustrate it with a special type of color critical graphs. One of perhaps the easiest one, the odd cycle, which has chromatic number 3, and removing any edge, make it bipartite. We know that its extremal number is exactly n squared over 4, the same as triangles. So step 1 is done by Erdős and Szymonovic, saying that the extremal number of odd cycle cannot be much more than n squared over 4. We can take any epsilon here, right? n squared over 4 plus epsilon, as long as n is sufficiently large as a function of epsilon. Then the second step is also done. I just extracted these from the Erdős-Szymonovic stability, saying that if you have a if you have a graph without an odd cycle and you are close to the extremal bound, then you are very close to bipartite. We can make it bipartite by removing 3 alpha n squares. So how do we use this structural information to slowly remove imperfection to make it exact? So the idea is we start with a max cut. What does max cut mean? That means the number of cross edges is maximized. Then what we can use about this information is that the number of edges inside is at most this 3 alpha n squared, right? There are not so many edges inside, because max cut is the one that are closest to editing it to bipartite. Now what we're going to do is to show, our goal is to show inside this max cut, actually there's no edge at all in X nor in Y. Then we are done, because that would imply that G is bipartite on the bipartition X and Y. So obviously the number of edges of G is at most n squared over 4, the bipartite Turon number. Okay, but sometimes we cannot do it all at once. So this is what I mean by slowly removing imperfection. So slowly we prove stronger and stronger results. First, we try to say that X and Y in this max cut, because our size is quite close to n squared over 4, they must be quite close to balanced ones. Then we show that, okay, we don't know whether there's an edge inside, but at least we know you don't have a vertex of high degree inside. After this preparation, we can then finally show that there's no inner edges. So let's see these details. Proof. So let let G X be an extremal M vertex extremal C2K plus 1 free graph. So the lower bound is easy. E of this is at least n squared over 4. This is easy just by taking two-round graph on two parts. So our goal is to prove that this G of EX, the extremal graph, has at most n squared over 4 edges. First, we're going to do our usual trick to boost to add additional minimum degree assumption. So how do we do that? As we've seen before, we keep removing low degree vertices to boost it. So first step is to boost mean degree. So how do we do that? We start with, let's let G n be our starting point, Gx, n vertex graph. And we do, so this is the algorithm, do the following. Remove, maybe we say for how do I write it formally? Okay, let me just write it informally for now. Do the following. If there exists a vertex V, let's call Vn, in V of Gn, with minimum degree, with degree maybe, let me make this capital N for now. So boost the minimum degree means we want to find a graph G in G X such that the mean degree of G is at least 1/2 minus epsilon times the order of G. All right, so how do we do that? If we don't have, if Gx itself satisfies the property, we are done. So that means Gx must contain a vertex, let's say V capital N with degree less than that, with in Gn, the vertex of Vn is less than 1/2 minus epsilon times n. Okay, so remove it. Let Gn minus 1 be Gn, remove Vn minus 1. and continue. So basically the general step is, so if it exists Vi in V Gi with dGi, Vi is less than 1/2 minus epsilon times I, then we're gonna let Gi minus 1 be Gi minus Pi. So whenever you have a small degree vertex, remove it. We proved that it must terminate at some step with the desired graph G. Otherwise, we claim that this process must terminate with a desired graph G. So why is that true? Well, suppose, let's prove this. Suppose at the end, let's call GK, okay, at the K step. So GK is the graph we obtain at the very last step. Remember, this sub-index K is the number of vertices we have. How do I write it? Maybe I want to I think I'm messing up the index. Give me a second. That's fine. Okay. So let's count the number of edges in the final graph. So E of GK is at least what? We start with the number of edges in GX, the extremal graph, which has at least n squared over 4 edges. And then we minus, every time we remove a vertex, we remove less than this many edges. So minus the sum of I equal to 1 to K 1/2 minus epsilon capital N plus 1 minus I edges. So that's how much we remove every time. Okay. And so if you expand this, blah, 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 I expand it for you. This is n squared over 4 minus 1/2 minus epsilon, capital N, K plus 1/2 minus epsilon, sum of I equal to 1 to K, I minus 1. Now write n to be the number of I know what's wrong. I messed up with the index. So actually, let me call this guy G0. Sorry. Let me check what will be the index. Let's say you start with G0. You remove a vertex V0. Okay. Let G1 to be V0 minus G0 minus V0, and there at the that's at the
Maybe just change the index k to n minus k.
So here V at I step, there exists Vi minus 1 in GVI minus 1, and you have something like this. And the number of vertices now is m minus I minus 1, probably something like this. Okay, please check. Then we're gonna let gi to be gi minus 1 minus bi minus 1. Okay, so after this relabeling, what I'm written now is it should be correct. So let n to be the number of vertices in gk. So now the subindex k is not a number of vertices in gk. It's a number of steps we proceed in this procedure. So this is exactly m minus k, right? If you proceed one step, you remove one vertex. You proceed k step, you remove k vertices. Now you rewrite this, blah, blah, blah. This equals to capital N is little n plus k minus, just plug this in there, little n plus k, k plus, this is the same term, no change. And then it equals to, there's some further calculation, but after you calculate dot, 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 you will get this number, n squared over 4 plus epsilon n k plus epsilon over 2 k squared plus some big O of k term. So this is some absolute constant times k, and when k is large, this is low order term, so you don't have to worry too much. So let's just look at this major term. Okay, so when k is linear in capital N, which is linear in little n as well, okay, what do we get? We get that this number is at least n squared plus 4 plus little o n squared. Okay, so this is linear in little n. We have this. But by Ehrlich-Stone-Shumanovich, we know that C2k plus 1 free graph on m vertices cannot have more than this many edges. So that's a contradiction, contradicting Ehrlich-Stone-Shumanovich. Okay, so we obtain what? We obtain a little n vertex graph G, which still C2k plus 1 free with a minimum degree condition. Let's write it here. So now we have n vertex graph G, which is a subgraph of Gx, which is C2k plus 1 free, and minimum degree of G is at least 1/2 minus epsilon times little m. Good. We're gonna now take this max cut on G. So this is our max cut. We have some edges going across. There's some edges going across, and you have some edges inside. Okay. Perhaps you have some edges inside. We want to show that there's no such inner edges, the red ones. So how do we do that? Well, let's first control the size of x and y, as we said. They must be close to n over 2. First of all, as this is max cut, and apply the stability on G, what do we know? Well, E of G, this mean degree implies E of G is at least n squared over 4 minus epsilon over 2 n squared edges. So remember, stability says if you are alpha n squared close to the extremal number, then you are 3 alpha n squared close to bipartite. That means the number of edges inside x and y is less than 3 times the distance, implying that EGX plus EGY, first of all, is less than 3 epsilon over 2 n squared. Not so many edges inside, which now we can imply that x and y must be close to n. This implies x and y must be n over 2 plus minus some error term, slightly larger than epsilon. So why is this true? Well, let's prove this claim. The idea is if xy is very skewed, you actually lose a lot of edges, cross edges. So we're going to fall below the promised bound on the number of edges of G. So otherwise, E of G is at most number of cross edges, which is xy, so you're losing too much, plus the inner edges. And we have a control on inner edges, right? So this is less than, if xy falls out of this range, their cross edges is at most this plus that times this minus that, which is n squared over 4 minus 4 epsilon n squared, plus the cross edges, which is at least at most this many. There's no square here. But this is strictly less than n squared over 4 minus epsilon over 2n squared, which is the bound we promised. So contradiction. So xy is about the right size. Now, next step, we're going to prove that there are not so many, no high degree vertex inside. Okay. How do we prove that? Well, let's draw some picture to illustrate. So if you have lots of degree here, next claim is that the maximum degree on the inner part is at most 2 square root epsilon n. Proof? If not, that means you have a vertex. Its inner degree is quite high, right? This is bigger than what we claimed. Remember, we start with a max cut. Max cut means the number of cross edges is maximized, which also implies that for every vertex, including this x, the number of neighbors going to the other side is at least as large as the number of neighbors it has in its own part. For otherwise, you could have moved x to the other side to increase the number of cross edges. Suppose not. So we have x in x where the degree of x in x is at least more than square root of epsilon n. Max cut implies the degree of x in y is at least the degree of x in its own part, which is also large, right? Let's give them a name. So this is the cross part. Oops, let me not. So let's call this what's the name? X prime, this is Y prime. So let this be X prime. The neighbor of X and Y is Y prime. Where is the contradiction? Well, the contradiction is that because the graph does not have an alt cycle, this will imply that between X prime and Y prime, there's no long path, which force X, Y prime, Y prime, X prime, Y prime to be very sparse between them. So we lose, and since both of them are quite large, we lose a big chunk. You create a large hole between X prime and Y prime. So the number of edges of G again falls below the bound we claim to have. That's the contradiction. So the proof is as G is C2K plus 1 free, this implies that G between X prime and Y prime, the bipartite graph, this G X prime Y prime is P2K free. Okay? If you have a P2K here, which together with X will form a C2K plus 1. Here, let me mention results we will use by Erdős and Gallai, which says that the extremal number of a path on T vertices is at most T minus 2 over 2 times n. Okay. By the way, this is optimal. So I should have mentioned this separately before. So this is optimal when T minus 1 divides n, because your graph G could be just disjoint union of clique on T minus 1 vertices. N over T minus 1 many. Okay, this graph has this many edges. Obviously, there's no path of length with T vertices. So using this bound, what do we know? We know between X prime and Y prime, the number of edges is only linear in n. Think of K as a constant, right? So now let's count the total number of edges in G. So E of G is at most well, there's inner edges. So let's write the inner edges first. 3 epsilon n squared over 2. This is the EGX plus EGY. Now the cross edges. The cross edges, well, it's total is x times y. But we are missing something here. How many edges we missing? We are missing at least minus. You have x prime, y prime. Minus the extremal number. You don't have a path, right? So minus some k times n by Erdős-Gallai. Okay, so this is the number of missing edges between x and y. Let me remark here. This is number of missing edges between x prime and y prime. Now, which is at most 3 epsilon n squared over 2. X times y is at most n squared over 4, no problem. Plus kn minus x prime, y prime are both larger than 2 square root epsilon n. So their product is at least 4 epsilon n squared. So again, we arrive to a contradiction. So, so let's summarize the properties of G. We have that the max cut satisfy that is very close to n over 2 size. We also have that, okay, the minimum degree of G is at least 1/2 minus epsilon n. We also have that the maximum inner degree is small. We're going to use these three properties to prove that now we shouldn't have a single imperfection. So let's draw this picture again, x, y. You have some edges going across. Let's try to prove that under this condition, we cannot have an edge at all. So let's call this edge, suppose you have it suffices to show no edge in, no, not it suffices. We now show no edge in x or y. By symmetry, let's just consider x. Suppose you have an edge. UV in x form an edge. Okay. So well, first of all, let's estimate for any vertex in x, let's estimate its degree to y. Okay. For any vertex little x in x, let's consider its degree to y. Its degree to y is what? It's the minimum degree of the graph G minus the maximum inner degree in x. Which is at least 1/2 minus epsilon n minus 2 square root epsilon n. So this is bigger than 1 minus 10 square root epsilon times y. Okay, using these two, we can prove this. So every vertex is almost full. Full degree to y. This is the proof. Now we're going to pick k minus 1 vertices. If you have UV edge, you pick arbitrary W1 to WK minus 1 in X minus U minus V. Okay, not U and V. You pick something else. So here, let's consider K equal to 3. So we are C7 free, C2K free. So you pick W1 and W2. What do we know? We know that all vertices in X is almost full to the other side. So all these 4 vertices, their common neighbor is almost everything. So we have U, V, W1 to WK minus 1 have at least 1 minus. There are K plus 1 vertices. Each vertex lose this much proportion of neighbors in Y times K square root epsilon times Y, which is still large if epsilon is small enough. So we can find the C7. They have lots of common neighbor, at least 3, right? At least 3. So you can pick 3 vertices, and it's easy to check that they contain a C7. C2K plus 1 in G, which is also in, that's a contradiction already. So we prove that G is bipartite. But we are not done. We're almost done. Because we need to prove Gx, the extremal graph. We pass from Gx to G, right? We only prove something about the subgraph. This is not a big issue because there was some slack we had. So we conclude that G is bipartite with bipartition X and Y. This makes cut. Now let's bound the number of edges in Gx, our original graph. We need to prove that our original graph is bipartite. This graph, number of edges, is at most the graph G, which is GK, the graph obtained after the K step. Remember that every step we remove a vertex, low degree vertex. To obtain the next one, to boost the minimum degree. And if you solve this, you sum this up, this is strictly less than n squared over 4 if sorry. Okay, maybe let me write one more. Okay, no. This is strictly less than n squared over 4 if n is strictly less than n. Meaning that if you're ever going to remove a vertex to obtain G, Gx will have less than extremal number of bound, lower bound that we know. So that means G is in fact the extremal graph Gx itself. We didn't remove any vertex at all. This implies Gx must be G. Gx bipartite. And if it's bipartite, the maximum number of edges is complete bipartite graph. That finishes the proof. Any question? Okay, so we're gonna see one more result on non-degenerate bipartite, non-degenerate Turing problem, and move on to degenerate ones. This is another classical result. Remember in the first homework, so the homework, we're gonna send the homework to this email, to the TA. So what's the email? Let me see. I type it in the chat. Homework to here. So send the homework to zhuo.wu at so the homework is still on March 28th, the first homework. All the homework in the future, just send it to this address. In the first homework, if you recall, one of the problems says in the homework, one of the problems says for any n vertex graph, triangle free graph, G, if the minimum degree of G is bigger than 2n/5, then G must be bipartite. Oops. Okay. This is optimal. The bound here, because we can consider this blow up of 5 cycle. This graph has mean degree exactly 2n/5, and obviously not bipartite and triangle free. So we cannot lower this number to 2n/5. Very good. So the last result we want to see, we're going to see is the extension of this exercise, which is a classical result proved by Anjashvai, Erlich, and Schorsch. Okay, so how do we extend that? It says that for every n vertex KR free, so RL is 3, graph G, if the mean degree is bigger than 3R minus 7 over 3R minus 4 times n, then G is R minus 1 partite. Remember, KR free graph, the extremal one is R minus 1 partite two-round graph. So this is saying when the mean degree is close to the extremal bound, then we remain R minus 1 partite. If you take R equal to 3, this is exactly 2n/5, extending the homework problem. We're going to give a proof. We give not the original proof. We give a short proof of this by due to Brent discovered later. Okay. One of the reasons I want to give this proof is there's a nice lemma proposition which extends this well-known fact that maximal triangle free graphs, if it's not bipartite, it contains a 5 cycle. Okay. Before we give this proof, again, I want to say this bound is tight. What's the tight example? So let me show you a trick. If for some triangle free graph, you have some extremal problem, you have some looks extremal, which is tight with some construction, then when you go to K4 free, instead of triangle free, all you need to do is just to add one more part completely joined to the previous one. Then this graph likely will maintain all these nice properties you have, in this case, minimum degree, and it's K4 free. because you just add one more part, and the original one is triangle free. If it's K5 free, you add one more part, so on and so forth, completely joined to the previous. A lot of the extremal problem, you just need to solve for the, or at least for the tight construction, you just need to come up with a triangle free one and attach new parts completely joined to previous ones for the lower bound construction. So this is the case here. So remark, the bound is tight. You consider this graph. So what is this graph? Well, just take, as I said, blow up of 5 cycle. Blow up of 5 cycle, completely joined to each other. And then we're going to add some new parts. Okay, so this is blow up of 5 cycle, V1, V2, V3, V4, V5, and the new parts, let's call it W1, Wi, How many parts we're going to add? If you don't have anything, this is K3 free. K4 free at one more part. So KR free at K at R minus 3 parts. We're going to make them completely join to each other. And between them, you have has all the edges going in between. Okay. You can optimize the ratio. I will tell you the ratio. Each one of these is of size n over 3r minus 4, same size. Each one of these is 3n over 3r minus 4. Okay. Very good. So how do we go about proving unjustified early shush? The clever idea of Brent's is the following structure, which he called 5 wheel-like graph. So definition of 5 wheel-like graph, which denoted by W. Oh, why is this also W? So maybe to not, let me try to not confuse you. Let me not use W here. Let me use U, capital U, capital U. Okay. So this is the wheel-like graph indexed by 2 parameters, R and K. Okay. How does this graph look like? Let me first draw the picture. So it looks like you have a top vertex V. You have a bottom edge W1, W2. So you have W1, W2 that form an edge. Okay. And we have 2 clicks. 2 R minus 2 clicks, complete graph. Let's call it Q1, Q2. So you have, oops. So let me, so this is Q1 and Q2 could overlap with Q1. Each one of them is a clique. With intersection size equal to K. So the K here is the number of vertices in the intersection. So here, intersection. And then we have all the edges from V. V is completely joined to Q1 and Q2. So all the edges Q1 to Q2. And we have all the edges from W1 to Q1, W2 to Q2. So W1 to Q1 looks like this. W2 to Q2 looks like this. That's the 5-wheel-like graph, WRK. Here are some examples. Let's see the simple one. What's W30? So you have a top vertex, you have a bottom edge, right? What's the size of the two cliques in the middle? The size is r minus 2, which is 1. And K is their intersection, is 0. So the two disjoint ones, clique of size 1. This is Q1, Q2. And W1 joined to Q1, W2 joined to Q2, V is joined to both of these two cliques. So that's 5 cycle. What's W40? Top vertex, bottom edge. Now the clique in the middle is of size 2, and they don't have intersection. So we're at this joint. V joined to both of these clique. W1 joined to one of them, W2 joined to the other one. So that's W40. What's W41? Let's draw one more. Well, almost the same. You have top vertex and bottom edge. In the middle, you have two clique of size 2, but now their intersection is size 1. So it looks like they have a common vertex. V, as usual, joined to everything. But now W1 is joined to these two. W2 is joined to these two. This is an actual wheel. So probably that's how he come up with this name. That's the structure. So, so the nice idea of the brands is that the nice also idea of brands is the following fact. Generalizing the fact that, so what we are generalizing, every maximal triangle free graph and non-bipartite so if you're not bipartite maximal triangle free, you must contain a 5 cycle. If this fact is not clear to you, prove it as an exercise. Okay? So how do we generalize this? Brands prove that this is a lemma proposition. call it lemma, for any G such that it's maximal KR free for some R at least 3 and non R minus 1 partite. Okay, when R equal to 3, we have all these hypotheses above. Then G must contain the not the 5 cycle, but 5 wheel-like graph. The one we drew earlier, we introduced earlier. The proof is simple. Let's prove it. First, if G is complete multipartite, graph, if G itself is complete multipartite, then the number of parts of G is at most R minus 1, as G is KR free. Okay, this is a contradiction because our graph is not R minus 1 partite. So G is not complete multipartite. Which implies if G is not complete multipartite, then its complement is not disjoint union of cliques. Its complement is not disjoint Actually, we don't need to do this. We just need to say G is not complete multipartite, right? So that means non-adjacency is not the equivalence class. It's not the equivalence relation. Non-adjacency is not an equivalence relation. Which then implies that G contains three vertices, V, W1, W2, such that W1, W2, such that V is not adjacent to W1, W2, and W1, W2 is adjacent to each other, is an edge. Okay? We must contain such three vertices. If this is not clear, think a little bit more yourself. Okay, if we have these three vertices, now we're going to use the hypothesis that the graph is maximal KR free. G is maximal KR free, meaning that we cannot add more edges while still being KR free. This would imply that in the co-neighborhood of V and Wi, for I equal to 1 or 2, contains a copy of K r minus 2. So let me draw it. In their co-neighborhood, there is a let's call it Q1. KR minus 2. Because if this is not the case, you can keep adding edges in the co-neighborhood until it contains the KR minus 2. We are still not creating any copy of KR, contradicting to the maximality of G. Similarly, let me draw in color blue. You have something like this in the co-neighborhood of V and W2. And that's it. That's 5-wheel-like graph. Okay, the co-neighborhood contains a Q1, for otherwise G plus VWI is still AR free, contradicting maximality of G. The proof is very simple. How are we going to use this to prove AES? So now we can give this short proof. So we're going to prove of this unjustified early short, which says that your minimum degree of G is bigger than 3r minus 7, 3r minus 4 times n, and you are KR free, then you must be r minus 1 partite. Okay, so actually we may assume G itself is maximal KR plus KR free by adding edges, because that does not harm this mean degree condition. You only increase mean degree. You can only increase. So by adding edges, if necessary, we may assume G is maximal KR free. Then the lemma that we prove above implies apply on G implies that G contains a 5-wheel-like graph WRK. There's one thing I forgot to say in this definition. Here we require these two are disjoint clique. Distinct clique. So this clique has r minus 2 vertices. That means their intersection must be strictly less than r minus 2. Otherwise, Q1, Q2 are the same clique. So we define WRK for any k up to r minus 3. But k could be 0. So k between 0 and r minus 3. Okay. So coming back here, we have a wheel-like graph. Now, let's call this W. We'll copy W of this WRK. No. contains WRK, right? Then what we're going to do, we're going to pick a special one. We know there must exist some WRK. We're going to pick one of them that maximize the value K. Pick a copy of W, copy W of WRK with maximum value K. But K cannot be bigger than R minus 3. Okay. So this is our W. V, you have Q1, Q2, W1, W2, this is the picture. Basically, we're going to double count the degree sum for the vertices in W. Okay. That's the idea. But so we first define a set X, which is the common neighbor of the intersection of the vertices in the intersection of these two clique Q1, Q2. Okay, so what is X? This is X. X contains all common neighbors of this part. U1 intersect U2. V is, you see I put V in here because V is common neighbor of Q1 intersect Q2. So V is a vertex in X. We're going to bound, we will bound the size of X in two ways. Okay, the first way is by double counting degree sum in W. Remember, this is our W. Double count is degree sum. So how do we do that? Well, to double count the degree sum in W, we have to control how, when you pick a vertex, how much edges it sends to W. What's its degree in W? An easy bound is that, here's an easy bound. G is KR free. Okay. And W contains KR minus 1. Because, for example, this is a KR minus 1. This is also a KR minus 1. It has plenty of KR minus 1. So that means we cannot have a vertex completely joined to W. If it's completely joined to W, you will get a KR. For any vertex V, V is not completely joined to W. Okay, so let's write P to be the number of vertices in W. This implies that the degree of any vertex V in W is at most P minus 1. You cannot be joined to everything. this easy bound is not enough to for our purpose. We're going to improve it a little bit. We're going to say if your vertex is not any arbitrary vertex, but the vertex in X, then actually you can improve this a little bit. Your degree in W is at most P minus 3 instead. So claim for any vertex X in X, the degree of X to W can be improved to P minus 3. Okay. How do we do that? Let me copy this. Okay, let's try to prove it. First, notice that, so if we have some X, we pick some X here in X. Let me see. Okay, first we notice that G is KR free implies what? Implies that remember each Q together with the corresponding W is a KR minus 1. So X cannot be completely joined to this set because G is KR free. So X has a non-neighbor in QI union WI for every I in 2. Okay. So let's consider the first case. If case 1 is if X is adjacent to V. So suppose we have an edge between X and V. Okay. Then same as this reason, V and Q1 and V and Q2 so actually I can write this, right? In Q union WI, QI union V, okay? This is R minus 1 click. 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 So in all these R minus 1 click, X must have a non-neighbor. Okay. Now, since X is adjacent to V, the non-neighbor of X in this R minus 1 click must be in Q1 minus Q2. So we must have, by the above observation, we have X has a non-neighbor, say Y1 in Q1 minus Q2 and Y2 in Q2 minus Q1. Okay, so X has a non-neighbor here. y1, non-neighbor here, y2. No problem. We are reaching a contradiction. Why? Now consider, let's redraw this. You have v here. So the contradiction is, if you consider v, and this is bottom edge, w1, w2, now I move x inside here. I increase the intersection size by 1. Then I can delete y1, y2 from q1 and q2. We obtain, again, a 5-wheel-like graph with a larger value of k, intersection size. So consider v, w1, w2, q1 prime, q2 prime, where qi prime is what? Is qi minus yi plus x. Okay? We get a copy of w r k plus 1, which is contradicting the maximality of w. Remember, we choose w so that k is maximized. So it's impossible to get a wheel-like graph with larger value of k. So that means x, any vertex in x cannot be joined to v. Okay? So this implies x is not joined to v. Okay? But again, by this assumption, it has a non-neighbor in here, which cannot be in here because x is a common neighbor of this intersection. So it can only be on this set and this set, two disjoint sets. So you're missing 1 degree here, 1 degree here, missing a third degree here. Together, you miss 3. We are done. For the claim. Okay. So we can bound vertices in X with a slightly stronger bound. Now let's double count the degree sum in W. The degree sum in W we have W in W. This obviously is bigger than you have P vertices. Each vertex, we have a mean degree condition. It's upper bounded by every vertex in X. We know that it has degree at most P minus 3. To W. And every other vertex has degree P minus 1, right? Actually, what we're writing here, this is degree sum of vertices to W. Degree sum to W it's the same as degree sum to vertices in W. Okay? So this is our first inequality. Now, remember our second inequality, which give a bound on x. Now we're going to bound x in a different way. In the second way, on the other hand, just simply by pigeonhole, xs is the common neighbor. Remember, x is common neighbor of Q1 intersect Q2. So x is Q1 intersect Q2. This is common neighbor, so they are complete to each other. Then we can get that the size of x is at least, how do we bound x? Well, there are k vertices in here, each sending out this many. So this is the degree sum of the vertices in Q1 intersect Q2. The excess of this amount over k minus 1 times n is the number of vertices that sends at least degree k to Q1 intersect Q2, which is exactly the common neighbor of Q1 intersect Q2. So this is the second one plus two implies that delta G is at most 2R plus K minus 4. This is some calculation times N, which is at most because K is at most R minus 3, 3R minus 7, 3R minus 4N. This reached the final contradiction because we assume our minimum degree is larger than this. Any question? So let me end today's lecture by some further comments. This is, as I said, the last result for dense Turon type problem. So what can we go beyond AES, the unjustified early short? The answer is yes. So here we find the lowest mean degree condition while maintaining being R minus 1 part-typed. So a relaxation is we don't need to maintain being R minus 1 part-type. We just need to maintain having a bounded chromatic number. Then how much we can lower the mean degree. So what I'm saying is AES is saying if you have n vertex triangle free, minimum degree can be lowered to as small as 2n over 5, then we still have bipartite condition. But this bipartite is the same as chromatic number is at most 2. So how much further we can lower these if we only require the chromatic number is bounded? This is the question. How much can we lower the mean degree if we only require a bounded chromatic number? Well, the answer is n over 3, but we're not going to talk about it here for now. So this is the problem called chromatic threshold. Okay. Later, we're going to talk about it. not for now. So next time, oh, let me make some further comments on dense Turan type problem. So there are extensions of this Turan type problem. So what's the extension? Let's define extremal n gamma h to be the maximum number of copies of gamma in an n vertex H free graph. Okay, what's the difference? Before we cared about maximum number of edges in H free graph. So now we replace counting edges to counting gamma. So our usual extremal number in this generalized setting is just extremal nk2 of H. Okay, so this is more generalized setting, also well studied. In particular, Erdős. Here I write Zykov, but I'm not sure. Zykov is in there. Please check. Erdős Zykov solved the clique case. What does it mean? This means for every s less than t, if you want to maximize the number of ks in the graph that does not have kt, then this is maximized again by Turan graph on t minus 1 parts. The same as when s equal to 2. Okay, some further references. For example, along Hellman in 2016 has some systematic study on this generalized Turan function. And the cycle problem is solved by Gish-Berliner and Shapira, who also make connections to regularity lemma. And there's also a nice one by Andrei Dresik, independently Atami, Belatsky, Dan Grau, Sergei Nurin, and Rasborov, who proved that in the triangle free graph, if you want to maximize C5, the maximum is n over 5 to the 5, where the optimal is balanced blowup of C5 with n over 2 vertices on each side. It's triangle free, and C5 is this many. Okay. Maybe let me finish today's lecture with two famous conjectures, which are still open. Which can be put into this generalized setting of Turan problem. There's actually some prize money, $250 if you solve them. The first one is called sparse halves. And for any n vertex triangle free graph, G contains a sparse half. What does it mean? Contains a set of n over 2 vertices inducing at most n squared over 50 edges. The number looks a little bit strange, but it's optimal. Best possible if true. Consider again blow-up of C5. Okay, you need in this graph, there's no n over 2 sets of vertices inducing less than n squared over 50 edges. So this n squared over 50 is the best number. You cannot put anything smaller. Another very related one, which is also open, is that for any n vertex triangle-free graph with the same tight example, if true, is that we can make it bipartite, can be made bipartite by removing n squared at most n squared over 25 edges. Okay, again, you cannot put anything smaller here because this graph requires n squared over 25 edges. You have to break everything here to make it bipartite. Question?